Welcome to the Politics of Everything. I'm Amber Daines, your host and podcast producer. This is a half hour of power, a podcast dropping every week where I unpack the politics of everything, from money to motherhood, nutrition to narcissism, startups to secularism, the environment, quality, and much, much more. Our guests are seasoned in the field or topic of their choice, even if you've not heard of them yet. This is a non-partisan show. So while I love exploring varied views and get a buzz from a healthy debate of ideas, this is not a purely blue, white, green program. Please subscribe, tune in and enjoy the politics of everything. Professor Tamara Davis is an astrophysicist at the University of Queensland with over 2 decades of experience studying the dark side of the universe, black holes, dark matter and dark energy. While leading major international surveys, she also tries to figure out deep questions such as whether dark energy can be used to make hoverboards and if time travel is possible. She's an avid communicator of science, an occasional host of ABC TV's Catalyst, including the American Institute of Physics Science Communication Award-winning Black Hole Hunters. Amongst her accolades are the Astronomical Society of Australia's Ellery Lectureship for career contributions to astronomy, the Australian Academy of Science's Nancy Mills Medal for Outstanding Female Leadership in Science, and an Order of Australia. She loves sport, and in her spare time, she's captained Australia at the World Championships for ultimate frisbee. That sounds pretty awesome to me. She's currently leading the Australian arm of the International Dark Energy Survey and will soon be taking on a new role as Deputy Director of the Australian Research Council of Excellence for Gravitational Wave Discovery. Plus, we went to high school together, so there's a fun fact for you. So welcome, Tamara, to the Politics of Everything.
Thanks so much for having me.
Go to zencastr.com/pricing and use my code, the politics of everything 30, all one word, and you'll get 30% off your first 3 months of Zencastr Professional. I want you to have the same easy experience as I do for all my podcasting and content needs. It's time to share your story. Okay. We did go to school together, and obviously you're always a smart student. I knew that. But did you, as a kid, did you want to be a scientist, or did you have some other dreams when we were at school together?
I don't know. I don't think I really knew what I wanted to be when I grew up as such. I wasn't one of these people who was like, oh, I want to be an astronaut, an astrophysicist when I grow up or something like that. I did have the idea of being an astronaut. That was one thing.
Yeah, that's pretty cool.
Yeah. But I also really, when I was really young, I remember I told my parents that I wanted to be an astronaut or a bricklayer.
Wow, that's quite, because the practical side of each appealed to you. What was it in that for you?
I really liked Lego.
Of course.
That's what I thought a bricklayer was. But anyway, yeah, no, I had not too much idea what I wanted to do when I grew up. And I think I'm one of these people that just finds everything interesting. There are so many interesting things in the world that when I went to university, I just chose – I was obviously pretty good at science and maths and stuff, and I liked those things, and I liked science fiction novels, and I loved learning about the space program and that kind of thing. So I just did the subject that gave me the most flexibility when I went to university that was sort of in those areas, and that was physics, and astronomy was a cool part of that. And then I followed my nose and did the most interesting thing in front of me at every point, and somehow ended up with a PhD in astrophysics.
Excellent. Well, definitely found your sweet spot and your specialty given all the accolades that you have achieved and, of course, the roles you've held. For most of us, the term the dark universe, we're not quite sure what that is. Some of us know Star Wars, we know the dark side. But what does it really mean for us in the non-science world?
Yeah, so the dark side of the universe. So I never realized when I was growing up and watching Star Wars that I would actually genuinely be studying the dark side of the universe and essentially the Force when I grew up. The dark universe, from my research perspective, refers to the parts of the universe that we can't see. So we look up in the night sky, we see stars, we see distant galaxies, which these big collections of stars, they may be big spiral things like our Milky Way or elliptical galaxies. We see all these bright things, but there's a lot of dark stuff out there. We expect there's like dust, stuff that just doesn't glow in the optical light that we can see with our eyes. But then as the years have gone by, we've discovered using astronomy that there's actually a whole heap more dark stuff out there than the kind of stuff that we might have thought. So black holes are one example of something that doesn't glow, but we know they're there. We can tell they're there because we've seen their gravitational pull, and we can see them moving around stars and gas and things around them. But there's these other two things that I study. One is dark matter, and it's something that is not made out of the same kind of stuff as you as me. It's not made out of atoms, but we can tell again that it's there by its gravitational force. And the other is dark energy, which is something out there that might actually be the energy of the vacuum itself that is accelerating the entire expansion of the universe and pushing galaxies away from each other. These two things, the dark matter and dark energy, we don't know exactly what they are. We can see their properties, but we don't know what they're made of. And so those are the two things that I spend my career studying.
How do you actually get to specialise in these particular areas? You know, what's the prerequisite, I guess, to understanding this? Because a lot of what you're describing sounds like it's not as known. There's mystery around it. You said some things we can't see it, but obviously there's metrics around knowing it exists. So how do you actually prepare yourself to do this kind of study?
I think the main prerequisite is curiosity and enthusiasm. So when I was doing my undergrad in physics in the late 1990s, dark energy was just being discovered. And basically the way that I describe how these things are known about is if you look outside and you see leaves of trees blowing in the wind, you can tell that there's something invisible out there pushing them, the wind. You can't see the air, but the leaves of trees are moving for some reason. And actually, if you go back a couple of hundred years, we did not know what the wind was. We didn't know what carbon and oxygen and nitrogen were in terms of their particle nature. We didn't have the periodic table. And we basically didn't know what this invisible stuff called air was, but we can really tell that it's there. And similarly, the motion of galaxies out in the depths of the universe, we can see them effectively blowing around in the dark matter and dark energy winds. So we can tell these things are there. We just don't have the periodic table of dark matter yet to be able to tell us what it is.
That's going to be your next project, surely.
Yeah.
With a team of people, I imagine you sort of obviously work with other people in this space as well. Is that correct?
Yeah, exactly. So I was super lucky with the people that I got to work with. I got dragged into some of the leading groups in the world that were the people who had just discovered dark energy in the late 90s. And I got to work with them throughout, I guess, most of my career. And things that we're doing at the moment are trying to measure its properties more precisely. And it's actually a super exciting time right now because this month we expect to unblind some of the data that we've spent the last 10 years taking and analyzing. And we do, like in medical trials where they do blind analyses where neither the doctor nor the patient knows whether they're getting a placebo or the real drug. We do blind analyses in cosmology as well, where we don't look at the answer because we know sort of how we expect these things to behave now. And so we do this whole big analysis, and then at the end we sort of take the lid off and see what the answer is. And this month we expect to be opening up the lid and looking at what the Dark Energy Survey has discovered after, for me, what's been 10 years of effort. So it's going to be very, very exciting when we're specifically measuring how dark energy behaves at great distances.
It's certainly not a job for anyone into instant gratification by the sounds of it. 10 years, my goodness.
No, indeed. Yeah.
What role does this dark universe play for us here on Earth? And in a practical way, what does that really look like? Are there some examples that can kind of, I guess, describe for us the importance of what you do? You wouldn't be doing this life's work if you didn't think it was important, but how does it impact us humans, if you like?
Yeah, great question. So the reason that we didn't discover dark energy centuries ago is because its effects here on Earth are actually super weak. The gravity here is attractive. The thing that has been discovered is that gravity outside on the universe scale is repulsive. It's pushing instead of pulling. We've basically found something out there that has some sort of anti-gravity property. The question is, what is that? And, can we harness it? Is that something that we can use to make different types of propulsion here on Earth, for example, to escape the gravitational well of our planet? Can we actually use this in rockets or something like that? This is where the sort of, we jokingly say, we're investigating, can we make hoverboards because we're looking at, can we harness gravity and make it work in reverse? Now, that's sort of crazy, and I do not expect to be able to do that in the course of my career. That's a really long-term goal of understanding the fundamental physics that goes on with it. And from the fundamental physics side of things, we're trying to get the next theory that will improve on Einstein's theory of gravity and our theory of quantum physics that does all the particles and stuff. We know those two theories can't be complete because they don't work together very well. So we're trying to get that next theory of gravity and next big theory of physics. Now, I know that might not sound very, important to the everyday type of person, but they're the kinds of thing, some of the reasons that we do it and some of the reasons that we get a lot of government funding to do this is not only for the fundamental physics reasons, even though that will advance things like the gadgets you can make in your phone and stuff, but for the kind of spin-offs that you can get, as well as the people that we train in high-end data science and image analysis and all sorts of different techniques. So yes, like some specific examples. Do you reckon you've used general relativity in the last week?
This feels like a trick question, Tamara. Honestly, I'm sure I have. What have I done? Have I unstacked the dishwasher or something? Is it really mundane?
It is something pretty mundane. Have you used a map that uses GPS with a blue dot on it?
Of course, yes.
Well, one of the cool things that I study and this general relativity theory of gravity is that time and space can warp and bend, and clocks will tick at different rates in different gravitational wells. So a clock here on Earth goes at a different rate to a clock up in space. And this sort of was discovered by studying black holes. But it becomes very practically important when you use GPS because the satellites for GPS are up in space. They're moving fast and they're in a different gravitational field to us here on the surface of the Earth. So if we didn't take that into account, the little blue dot on your map would be wrong. So every time you use your GPS, you're using general relativity.
That's cool and pretty wild at the same time. So obviously you've been in this space for, 20 plus years in your career. How's this kind of research changed over time? I guess you get to know more, get to understand more because of the research that you do. And things like funding you mentioned before, but are there other factors which really impact, I guess, the speed and the velocity of what you're doing? How much more you can find out? Like what would actually help it propel into the future as well as, I guess, how it's changed over time?
Yeah, well, there's two major aspects. One, we need to advance the theory, and the other is we need to get better observations. The thing that has changed over the course of the last, say, 30 years just enormously is the quality of the observations that we're able to get, because our telescopes and the advent of digital cameras has dramatically advanced what we're able to observe. So particularly digital cameras, which actually is another example of things that astronomy has pushed forward. So we wanted to get really accurate images of the sky. And so some of the first users and developers of digital cameras were the astronomers trying to put them on their telescopes. And that obviously has spilled over in a big way into all sorts of things that we use in our modern everyday life. But, back in the 1990s, we were only able to see a small distance out and with small fields of view, so little patches of the sky. And it took decades, many, many decades, to do the first full map of the southern sky, or looking at a map of the entire sky. And now we've got telescopes that are going to be able to do that that can already do that in a couple of days. And so we're now able to, with something, the Vera Rubin telescope over in Chile is going to be opening soon, and that will be measuring the entire southern sky every few days. And that will mean that we're no longer looking at space as just a static thing. We're looking at it as a dynamic thing. We can see things changing. And particularly important for me, I study the way that we measure dark energy. One of the ways, the way that I'm involved in, is using supernovae, these exploding stars. And so when they discovered dark energy in the late 1990s, there was two teams that both worked for almost 10 years, 5 or 10 years, to discover between them 52 supernovae. And with the release that we're going to have this right now, this month, we're expecting to have about 2,000.
Wow.
And so just But even that dwarfs in comparison to some of the other things. That this same project I'm working on, the Dark Energy Survey, released a catalogue of 590 million galaxies. So we observed over half a billion galaxies. And the vast quantity of data is phenomenal. We can basically see back to everything along some small lines of sight to the very beginning of the universe, because you're looking so far back in time when you look at these images in astronomy.
Wow. Great. I can't let this conversation go by without touching on, of course, the world of hoverboards, but really time travel. A lot of people put that into Hollywood movies, and it's something that's, anyone into sci-fi loves that idea of, whether you're a Doctor Who fan or something else. What does that really mean? I mean, you talked briefly about this idea that time, clocks, for example, tick in different universes very differently. Is time travel something that's real, and why? Like, why does it exist?
Yeah, well, obviously, the flippant answer is we're all traveling forwards in time right now.
Of course we are. As we speak, every second.
Yeah. And the fact that time runs differently for different people is a genuine thing that has been measured and clearly occurs. So in some movies like Interstellar, they use that as a good plot twist, where the people who go close to the black hole, which is a really strong gravitational field, their clock goes much slower than the one who stays in the spaceship. And so the guy that stays in the spaceship ages decades in the time that they spent an hour near the black hole. And so if you want to travel vastly forwards in time and see human civilization as it is tens of thousands of years from now, that's very possible. You can just jump in a spacecraft, accelerate away, and then turn around and accelerate back. And so, for example, if you just accelerate at an even pace, the same sort of acceleration that we feel here in Earth's gravity, and you just do that towards the center of the galaxy, you'd be able to get there in a human lifetime, even though the center of the galaxy is 25,000 light years away. So it takes light 25,000 years to get there. And you can do it in a human lifetime because you can slow down time if you're moving fast.
Wow, my mind is blown.
It doesn't change your subjective feeling of time.
Right.
You still feel like you're aging at the same rate.
Right, so a minute's still a minute, a year is still a year. Yeah, okay.
Yeah. But you can then chuck a Yui and come back to Earth, and you would be back at Earth about 50,000 years in the future. So you would be able to see, you could actually do that and come back and see Earth as it would be in the future.
Wow, that's wild. Do you just have to call Elon Musk to make it happen, or how does that work?
Yeah,
it sounds very expensive.
Yeah, the problem is trying not to hit anything at those speeds, but that one's definitely theoretically possible. The thing that most people want to do when they talk about time travel, though, is go back in time, and that one's much less likely to actually be possible. Partially because we haven't seen people traveling in time that we know of, and so if we haven't seen them, why not? If it's possible, why haven't they? It is mathematically possible to use black holes and wormholes. If you join like two black holes in sort of a weird warping of space-time way, mathematically it's possible to make a time machine. But the problem is you need some really weird stuff. You need like negative energy, and that's like saying that you have negative mass. So, I can go on a diet and lose 10 kilos, but I'm never going to be less than 0 kilos. I'm never going to be minus 60 kilos.
Yeah, you still have to have some mass, some body. Yeah,
and
absolutely.
So most of the solutions that allow time travel require something like negative mass. And so even though the mathematical solution is there, we don't think that they're necessarily possible. But every time a physicist says, "Oh no, that's impossible," you turn around and see someone doing it. So we're always hesitant to say absolutely not, that's not possible, because the maths there is some mathematically possible solutions there. Yeah, it's a bit complicated.
So you've done so much in this space since the late 90s, as you've articulated. What would you like to see next in your career phase, and like what direction do you think you might go forward in?
Well, I'm actually thoroughly enjoying teaching at the moment. And at the moment, I've got a really great research group here at the University of Queensland with a whole bunch of just awesome postdocs who are doing phenomenal work. And I'm so impressed with all of them. And leading that research group has been super fun. And we now have this new Centre of Excellence for gravitational wave discovery that is continuing on from some current centre, but I'm going to be taking over the deputy directorship of that. And that's going to be a fantastic 8-university centre that are all combining to do some really big question science. And so research-wise, I'm super excited to be looking at these gravitational waves in the next little while and try and understand more about dark energy and dark matter using those. But I'm also really enthusiastic about teaching and conveying my excitement about the universe to the next generation of physicists and seeing where they take it.
What's the best advice, either in life or business or anything really, that you've been given, and why? Why has it stuck with you, that advice?
I think actually genuinely some of the best advice is to not concentrate too much on work and studies.
Oh, that's ironic for you. I mean, I know in your spare time you do things like, captaining world championships, but yeah, that's an interesting thing. So for you, what does that look like? Why has that advice, kind of meant so much to you?
So I think that advice has been really important for me because you learn so much stuff from other people that you don't learn in a classroom or behind your computer. And when you're doing pretty much any job, I think a lot of the things that you have to do in that job involves dealing with other people. And being part of the collaborations that I've been part of and getting the leadership roles that I have arose because of my skills not only in astrophysics, there was astrophysics knowledge required, but primarily I would say because of the skills that I learned from coaching and captaining teams, from being in sports teams, and even leading budgets and stuff like that. I all learnt through sport before I applied them in astrophysics, and so I think there's so much to be learned there.
Yeah, absolutely. No, I think that's great, and I think most of us can relate to that as well.
Yeah, and also I'd also add that in terms of mental health and that kind of thing, and just keeping balance in your life. Sometimes the work will be going crap. Sometimes the outside of your life things will be going crap. But if you have a whole bunch of different things, it's rare that they're all going crap at the same time. And so it keeps you a bit happier when you have a bit of balance.
That is so true. You do, absolutely. If we spoke again in a year's time, obviously you would have started your new role, but what would be, say, a number one goal that you would have achieved and why? I imagine you are good at goal setting, considering all you achieve, but is there something particular? It doesn't even have to be in the space we're talking about in terms of the dark universe. It could be, a personal goal. Is there something you'd like to sort of keep yourself to account for on this show today?
You're going to come check back on me in a year's time?
I never do, but I probably should. I should do a whole series of that.
Yeah, I think I would really like to have finished up with this dark energy survey analysis and published new knowledge about what dark energy actually is. And as part of that also, we have a huge amount of the different sort of ways that our research can impact the world, and to see some of the research we're doing going out and impacting the world in different ways is also really, really fun. So I know one of the things I didn't mention earlier is that some of my collaborators are using the same image analysis software that we built to discover supernovae to build an app that lets people look at skin cancers and take pictures and see if they change over time, or look at their moles and be able to identify skin cancers and things like that. And so seeing that those impacts of the kinds of research that we do when you use it in novel ways is another very rewarding thing.
A final takeaway message for us today on the politics of the dark universe.
I actually think one thing that I find really important from studying astrophysics is just the perspective it gives on our earthly issues. So when I look at the pictures that are taken from Earth from outer space, and I look at the great vastness of the universe around us, you realize how rare and precious something like the Earth is. We've now observed thousands of planets that are around other stars. We know that there's lots of planets out there, but there aren't very many that are like Earth, and they're incredibly difficult to get to. And if there's any sort of take-home message, I think when I look up and I know that there's about 100 kilometers worth of atmosphere above us, that's all the air that we're ever going to have to breathe. And you look at Earth from a cosmic perspective, any of our sort of trifling troubles here on Earth are sort of fade into nothingness when it compares to actually what we need to do to look after our planet. And that might be my takeaway message, I think.
Yeah, I think there's a good one for all of us. And of course, if you do want to connect further professionally with Tamara, there will be some details on the show notes. It's been a fantastic conversation. And I think I've learned about 10 things today. So thank you so much for your time, Tamara.
Again, thanks so much for having me, Amber.
Thanks so much for listening today. If you've enjoyed the politics of everything, I thrive on your feedback. So please add a short review and share the podcast with your network through Apple, Spotify, and all the usual suspects. I'm always on the hunt for new and diverse guests, so if you or someone you know has a fresh idea you're busting to get out there, please email me at amber@amberdanes.com and my crew will get back to you very soon.